Okay, so this is one last example. I just want to review. This is n over 2 to the n power. So basically the series is 1 over 2 plus 2 over 2 squared plus 3 over 2 to the third power plus 4 over 2 to the fourth power dot dot dot. Okay, it goes on forever. So basically, if we want to use the ratio test, right, we have the limit as n approaches infinity of u to the n plus 1 over u to the n, right, all within the absolute value. So that's equal to the limit of n approaching infinity of, again, everywhere that there is, in our general term right here, anywhere that there is an n, substitute in an n plus 1 for this top term. So we get n plus 1 divided by 2 to the n plus 1, and all of that, okay, you could put that in parentheses if you want, is divided by, and then just the regular nth term, which is just n over 2 to the n, okay? Again, we get that from right here because that's the general term. Now, what we can do is, we can, when you divide by a fraction, it's the same as multiplying by the reciprocal, so we get limit as n approaches infinity of absolute value of n plus 1 divided by 2 to the n plus 1 times 2 to the n divided by n. Now, take note of this. When you have 2 to the n plus 1 and you have 2 to the n, okay, remember, if you have, I like to use examples. If you have 2 to the 5th power down here, or no, yeah, 2 to the 5th power down here and 2 to the 4th power up here, that's the same as, actually, let me write it out. Okay, look, if you have 2 to the 4th power over 2 to the 5th power, that's equivalent to 2 times 2 times 2 times 2 over 2 times 2 times 2 times 2 times 2, right? So basically all these cancel out except for this 1, 2 down here. So knowing that, we know that when we see this right here, 2 to the n and 2 to the n plus 1, that means that this here just has an extra multiple of 2, right? So therefore we can split this up into the following. Instead of 2 to the n plus 1, we can just write 2 times 2 to the n, right? And then I copied everything else over. Therefore, when you multiply this, it's 2 to the n in the numerator. It's going to cancel out this 2 to the n in the denominator, leaving you with the following, which is just, I wrote it down here, okay, because again, I crossed these out since they canceled, leaving us with the limit of n approaching infinity of the absolute value of n plus 1 over 2n, and then, ending the absolute value. Okay, so with this, what we could do is basically, using L'Hopital's rule, we could find the derivative of this term and the derivative of this term, and then find the limit. So basically, the derivative of n plus 1 is just 1, and the derivative of 2n is just 2. Therefore, we're finding the limit of n approaching infinity of 1 over 2, which is equal to 1 over 2. Okay, so therefore, the limit, which is equal to p, is equal to 1 over 2, which is 1/2, right? Thus, p is less than 1. Therefore, the series converges, and it's confirmed by the ratio test. Okay, and so that's the answer. And again, for this video, this series that I use in this video is referenced from Elements of Differential and Integral Calculus by William Anthony Granville and Percy F. Smith, published in 1904. And this, from what I understand, is a textbook in the public domain. Therefore, it's allowed to be used in these purposes. Thank you very much. Okay, that's all. Thank you very much. Bye.